Welcome everybody to the CANCID Webinar series. I'm really pleased this afternoon to be bringing the fourth webinar in this series. And we're really fortunate today to have Chin Xu with us. She's going to be presenting on irrigation of corn and soybeans in Ontario as an adaptation to climate change from 2020 through to 2070. My name's Rebecca Short, and I'm on the CANCID Executive. I'm really pleased to be kicking off this session today. Just a few housekeeping notes. We will be recording this presentation, and it will be posted to the CANCID CWA website afterwards. Everyone who registered will also receive a copy of the recording tomorrow morning in an email. We will be taking questions for this presentation after the session, but you can type them into the question area on your dashboard at any time, and I'll be reading out the questions to Chin at the end of the session. You're all in muted mode, but with the small group, we may have a chance for some discussion at the end. We'll see how things go. This is as I mentioned, the fourth webinar in our series from CANCID this year. The next webinar will be Willemijn Appels. We'll speak about center pivots and irrigation in center pivots in January. So we're looking forward to that presentation coming up soon. So I think without further ado, we're going to get right into the presentation. So Chin Xu is a sessional lecturer teaching natural resource economics at the University of Guelph. She obtained her PhD in food, agriculture, and resource economics at the University of Guelph, and her master's degree in economics and bachelor's degree in environmental science at Dalhousie University. Her research interests span both environmental and resource economics, as well as consumer consumption. Right now, her research focuses on the economic feasibility of using irrigation as an adaptation to climate change in Ontario crop production. So thanks so much, Chin, for being with us today, and I'll let you take it away.
Thank you, Rebecca. So hello, everyone. So thanks for attending the webinar today. And I also would like to thank Stephanie and Rebecca for arranging this webinar and invite me to present. So today, my presentation topic is about irrigating corn and soybeans in Ontario as adaptation strategy to climate change for 2020 to 2070. And this is my PhD project that advised by Glenn Fox. And now you have know who I am, and I'm going to turn off my cameras during the presentation to ensure the best internet performance. And I will turn on it again during the question session to discuss the question you have. This project was originated from the concern on possibility of having increasing water scarcity in rural Ontario. And in 2010, the provincial legislature passed the Water Opportunities Act. One of the provisions of the act is that OMEFRA may be required to set water conservation and efficiency targets for the agriculture sector to develop the policies and programs to achieve those targets. And for this reason, during 2014 to 2018, we have developed a special stochastic simulation model that is able to simulate the water use in crop production in Ontario to serve as a framework to study alternative water policy approaches for crop production. And based on that project, we upgraded the special stochastic simulation model to study the feasibility of using irrigation and tillage drainage as climate change adaptation strategies for Ontario crop production. And today, I'm going to introduce our results in terms of the irrigation part. If you are interested in the research about tillage drainage, I will be happy to provide more information during the question session. So in recent years, there are increasing concerns about the effect of increasing dry events on crop yield in Ontario. And since the moisture for for field crops are mainly from precipitation in Ontario, and irrigation is currently not widely used in Ontario crop production. So our main research question is, would irrigation be feasible as a climate change adaptation strategy for crop farmers in Ontario? To answer this main research question, we developed 5 sub-questions. The first question, we will look at the trend of corn and soybean yields under climate change. And then we will talk about if irrigation would increase the corn and soybean yields in a changing climate and by how much. And then we will talk about how many years the farmers would use irrigation within the next 50 years. That's the frequency of using irrigation. And then we will discuss, is it economically feasible for crop farmers to use the irrigation as a climate change adaptation strategy in Ontario? So under this question, we will see whether the benefit of irrigation outweigh its cost. And last, we will talk about how much water might be used for irrigation if it's economically feasible for crop farmers. So for the second and third question, we only consider the variable cost of irrigation. But for the last 2 sub-questions, we consider both the variable and fixed cost of using irrigation. And in my presentation today, I'm going to briefly introduce the research method first, and then talk about the results to each question. First, the method. In our project, we developed a special stochastic simulation model for county-level corn and soybean production in Ontario, and it includes 3 parts. First, we estimate the crop yield models for corn and soybeans based on the data from 1950 to 2013, and then we developed an economic theoretical model to determine the irrigation demand by using the profit maximization method. And last, the estimated coefficients in the crop yield models and the irrigation demand in the theoretical model are put into our simulation model to simulate the crop yields and calculate the irrigation demand for the time period from 2020 to 2070. And the special stochastic simulation model allows us to simulate crop yields in the time period, and last allows us to compare the benefits and costs of using the irrigation so that we know if irrigation is economically feasible in Ontario crop production or not. Here is a bit of more details about the special stochastic simulation model. We studied corn and soybeans production across the 29 counties in Southern Ontario. And the crop yield estimation includes both the climate and economic variables, including the factors such as precipitation during the growing season, the degree days during the growing season, the crop price, the fertilizer price index, the groundwater level, the land quality ratio, the CO2 concentration, and the time trend as a proxy of technological development. I'm not going to present the estimated coefficients of crop yield model today, but if you're interested in this part, I would be happy to answer a question during the question section. And a paper about it is just published this year. And for the special stochastic simulation model, we developed it in an agent-based software named NetLogo. The simulation model has 4 alternative climate scenarios. And the base scenario is the linear extrapolation of the historical climate trend. And the 3 climate change scenarios are based on the projection from composite GCM model with the RCP 8.5. If you are not familiar with RCP 8.5, it means the most extreme climate change scenario. So please look at the right table here. It lists the projected increase of global mean surface temperature for 2081 to 21,000 relative to the 1986 to 2005. And in the RCP 8.5, we can see the global mean surface temperature increases the most compared to the other pathways. And for the simulation model, we also use the Monte Carlo simulation method. It means that we take 500 random draws in each year for each climate variables in each county. This slide compares the 4 climate scenarios I just mentioned, and I hope this comparison could give you a better understanding of the results. First, the base scenario has the linear extrapolation of level historical climate and technology variables, and the constant real prices as well. The mean and standard deviation of the degree days during growing season increased by 0.2% per year, and the precipitation during growing season increased by 0.28% per year. And for the climate change scenarios, the data of the precipitation and degree days are from the Natural Resources Canada, which are based on their modeling of the RCP 8.5. And we use their fitted linear trends as the means of our Monte Carlo distributions. And in all climate change scenarios, the means of degree days and precipitation during growing season increased by 0.25% per year. And the standard deviation of the degree days increased by 0.25% per year as well. But the standard deviation of precipitation varies across the scenario because we would like to examine the effect of irrigation under more variable precipitation conditions. In the RCP 8.5 base scenario, which we also call it C1 for short, the standard deviation of precipitation during growing season increased by 0.25% per year. And in the RCP 8.5 with median increased variability of growing season precipitation, which we also call it C2 for short, the standard deviation increased by 1.25% per year. And in the RCP 8.5 with high increased variability of growing season precipitation, which I also call it C3, the standard deviation of precipitation during the growing season increased by 2.5% per year. This is an extreme case, since we would like to find out what results would be in the extreme condition. In climate change scenarios, we set different variability of the precipitation during growing season, because in theory, we believe that when the variability of growing season precipitation increases, there is an effect on the probability of the dry events and also the probability of wet events. So to explain it, let's look at the figure on the right. This figure shows 3 distributions of precipitation with the same mean but different variabilities. This green curve shows the distribution with the smallest variability of precipitation, and this red curve shows the distributions with the largest variability. And for the dry events, we define it as when the precipitation is less than 60% of the mean of precipitation in one county. So the area under the curve and to the left of this gray dashed line shows the probability of dry events. And we can see as the variability of precipitation increases, the probability of dry event increases as well. Events. We define the wet events as the precipitation greater than water required for potential yields for one crop. And the area under the curve to the right of this black dashed line shows the probability of wet events. And we can also see that as the variability of precipitation increases, the probability of wet events increase as well. So based on theory, the probability of dry events are expected to be higher in the climate change scenarios, especially in C2 and C3 scenarios, which have a larger variability of precipitation. So to show it, I take the Lambton County as an example. This slide shows the probability of dry events in Lambton County for 2020 to 2070, and the x-axis lists the 4 climate scenarios, and the y-axis presents the probability of having dry events. And in the figure, we can see the probability of dry events increases as the variability of precipitation becomes larger. And this result is based on the 500 Monte Carlo draws per year and per county. And this slide shows the probability of wet events in Lamp County for the next 50 years. And again, the x-axis shows the 4 climate scenarios, and the y-axis shows the probability of wet event. So from this figure, we can see that for both corn and soybeans, the probability of wet event increases as the variability of precipitation becomes larger. After introducing our method and comparing the climate scenarios, now I would like to talk about the modeling strategy in the simulation to help you understand how the simulation model works. This blue row shows the procedure when the irrigation is not used. And for each simulation run, we take randomly draw from the distribution of simulated climate variables and put those climate values into the county level crop yield models for each crops. And subsequently, we can calculate the simulated crop yields when irrigation is not used. And this yellow row shows the procedure when irrigation is used. So based on the random draw of precipitation during the growing season, we first determine the irrigation amount by considering the variable cost of irrigation. If the irrigation amount is 0, then it means irrigation is not required with that certain amount of precipitation during the growing season. But if the irrigation amount is greater than 0, then it means the irrigation is required in this case. And then we add the irrigation into the precipitation during the growing season as the available moisture for crops during the growing season. And next, we run the crop yield model to calculate the crop yields when irrigation is used. And then we can compare the crop yields between with and without irrigation, and find out how might crop yield increase with irrigation. And last, we can compare the net benefits from irrigation and the fixed cost of irrigation to determine if irrigation is economically feasible in Ontario crop production or not. This slide further explains the last step. How do we model the costs and benefits of irrigation to farmers? First, we define the net farm returns as the difference between present value of the sequence of annual changes in revenue from irrigation and the present value of irrigation total cost. If it's greater than 0, then it means the irrigation in the county is profitable. However, if it's less than 0, then the irrigation is not profitable in that county. And here, the annual change in revenue from irrigation is calculated as the difference in crop yields from the irrigation and multiplied by the crop price. And for the present value of irrigation total cost, it contains 2 parts. The first part is the sum of the present value of annual irrigation variable costs. And the annual irrigation variable cost equals to the sum of unit pumping cost, unit labor cost, and water price, and times the irrigation water quantity. And the second part is the present value of irrigation fixed cost. And it's the cost or building, and the value cost replacement occurs every 17 years. So that is at
Sorry, am I losing the connection?
Yes.
Internet connection?
Yes.
Can I keep? Oh, can I keep going now? Is it fixed?
Try again, Chin.
Okay.
starting. And 5.2% discount rate is used to calculate the present values of various revenue and cost. This slide shows how do we determine the optimal irrigation in each year. And briefly speaking, the optimal irrigation amount should be the difference between the water required for maximum profit and the precipitation during the growing season. But due to a time limitation, I'm not going to give more details. If you are interested in our method, I will be happy to answer your question during the question section. The previous slide shows how do we determine the optimal irrigation amount in each year, but the irrigation demand actually varies over time. So this slide shows the net annual returns per hectare from using irrigation for illustrative county over the studied 51 years. In the figure, you can see that the x-axis represents the year of simulation and the y-axis shows the net return to irrigation. And this result is from is not used. It might be because of wet events or the cost of operating irrigation in that year is higher. We can sum up of irrigation total costs, as I mentioned earlier, and see if the irrigation in the county is profitable or not in the one draw. This slide shows the cost parameters and their values in our simulation model. I have explained these parameters when I talk about the cost and benefit of using irrigation. To explain these parameters again. But one thing I would like to mention here is that since irrigation is not widely used for corn and soybeans yet in Ontario, the actual costs of irrigating the corn and soybeans in future are unknown. In addition, many factors such as the technological development and better irrigation management may change the costs of irrigation in future. So for each parameters, for each type of cost, we conduct sensitivity analysis to explore the results with alternative irrigation cost values. Now let's look at the results and recall that our first sub-question is how might corn and soybean yields be affected by climate change in Ontario? This slide shows the projected crop yield for 2020 to 2070 in Ontario. And in the figure, the x-axis shows the year and y-axis shows the crop yields. Each line shows the provincial acreage weighted average yields for one crop and one climate scenario. So in the figure, the upper panel is for corn and the bottom panel is for soybeans. And different color represent the different climate scenarios. Red is for base scenario, green is for C1 scenario, which represent low variation of precipitation. And the blue one is for C2 scenario with the medium variation of precipitation, and red is C3 scenario with the high variation of precipitation. We can see from the figure that both corn and soybean yields increase for 2020 to 2070. And in both figures, the crop yield in the climate change scenario with low or medium variation of precipitation, which are represented as the green and blue line, increase faster compared to the trend in the base scenario, which is represented as black. But in the scenario with high variation of precipitation, the corn yield increased lower than the base. And for soybean yields, the yield increased faster than the base until around 2065, but then increased lower than the base. Under climate change, people not just care about the trend of average crop yields, they also wonder how crop yields are vulnerable to climate change. So we also look at the variability of crop yields across the 4 climate scenarios. And this figure shows the provincial standard deviation of simulated crop yields for corn and soybeans across the 4 climate scenarios. And again, the x-axis shows the year and the y-axis shows the standard deviation of crop yields. And the climate scenarios are represented as different color as I have explained in the previous slide. And from this figure, we can see for both corn and soybeans, the crop yields in the base scenario, which are represented as the black line, have the lowest variation. And when the variation of precipitation become larger, the crop yields have larger variation. Except for the standard deviation of crop yields, we also calculate the coefficient of variation for crop yields over the 4 climate scenarios in 2020 and 2070. And again, in the table, different color represents different climate scenarios. And the second and third column shows the coefficient of variation for corn yield across 4 climate scenarios. The second column is for 2020 and the third column is for 2070. We can see that in all scenarios, the coefficient of variation of corn yields increase between 2020 to 2070. And the fourth and fifth column shows the coefficient of variation for soybean yield across the 4 climate scenarios. The fourth column is for 2020 and the fifth for 2070. We found that the coefficient of variation for soybean yields decreases between 2020 and 2070 in the base scenario, but increase in the C2 and C3 scenario. And the decrease in the base scenario is because that the standard deviation for soybean yields increases slower than its mean. And we're not surprised to see that the largest increases in the coefficient of variation in yields for both crops occurs in the C3 scenario, which is the scenario with the high variability of growing season precipitation. We are interested in the change in crop yields because it affects the crop revenue. So this slide shows the change in provincial crop revenue between 2020 and 2070 across the 4 climate scenarios. And here, the crop revenue is calculated by multiplying crop yields, crop price, and cropland area together. And we assume the crop price and cropland area are constant over the started 51 years. So from this table, we can see that for corn, the revenue would increase by from $170 million to $220 million per year from 2020 to 2070. And compared with the corn, the soybean revenue would increase slightly more. It increases by from $197 million to $249 million per year from 2020 to 2070. And the largest increase in crop revenue for both crops occurs in the C1 scenario, which has the low variety of precipitation. And the smallest increase occurs in the C3 scenario, which has the high variability of precipitation. Based on the above results, we can summarize these 4 key findings. First, we find that the provincial average corn and soybean yields increase under all 4 climate change scenarios that we studied. And in the C1 and C2 RCP 8.5 climate change scenarios, the both corn and soybean yields increase faster compared to the base scenario, but not for the C3 climate change scenario. And especially for the soybean yield, it increased faster under the C3 scenario compared to the base scenario until 2065. And after that, they increase slower than the base scenario. And in terms of the variability in crop yields, we find that the increasing variation in growing season precipitation increases the variability in both corn and soybean yields. After looking at the trends of corn and soybean yields under climate change, now we're going to look at our second sub-questions. How might irrigation affect corn and soybean yields in a changing climate? And we only consider the variable cost of irrigation in this question. First, let's look at the effect of irrigation on corn yields under the 4 climate change scenarios for 2020 to 2070. This figure has 4 panels, and the x-axis of each panel shows the year, and the y-axis of each panel shows the corn yield. And each panel represents each climate scenario. So we have base scenario, C1, C2, and C3. So in each panel, the solid gray line shows the trend of provincial average corn yield without irrigation, and the dashed black lines shows the trend of provincial average corn yield with irrigation. So in the figure, we can see that the irrigated corn yields are always higher than non-irrigated corn yield. In addition, the corn yields increase faster irrigation when the variation of precipitation during the growing season increases. Now let's look at irrigation effect on soybean yields. And again, in each panel, the x-axis shows the year and the y-axis shows the soybean yield. And the solid gray line shows the soybean yield without irrigation, and the dashed black line shows the soybean yield with irrigation. And we can see that the results for soybeans are quite similar with corn. We can see that the irrigated soybean yields are always higher than non-irrigated soybean yields. In addition, the soybean yields increase faster with irrigation in climate change scenarios, especially when the variation of precipitation becomes larger. From the previous 2 slides, we know that irrigation do improve the provincial corn and soybean average yield, but by how much? So in this slide, I made a table to present the change in provincial crop yields from the irrigation under the 4 climate change scenarios in 2070. The first column is the 4 climate scenarios, and the second column shows the change in corn yields. We can see that irrigation increased corn yields in the range from 2.4% to 11.1%. And similarly for soybeans, the fourth column shows the change in soybean yield, and the last column shows the corresponding percent change. And the increase in soybean yield ranges from 1.7% to 8%. So it seems that irrigation has larger effect on corn than soybeans. As I mentioned above, we should not only look at the mean of crop yields, but also study the variability of crop yields. And this slide shows the variability of corn yields without irrigation under the 4 climate scenarios for 2020 to 2070, which is developed from our answers to the first sub-question. And in each panel, we have the year on the x-axis and the corn yield on the y-axis. And this black line shows the provincial average corn yields over 51 years. And the gray shaded areas shows the 3 standard deviation around the average yield. And as I mentioned in the first sub-question, we found that the variability of corn yield increases as the variation of precipitation getting larger. Now let's look at how does irrigation change the variability of corn yields. This slide shows a similar figure with the previous slide, but this figure shows the results with irrigation. In each panel, the dashed line shows the provincial average corn yield over 51 years, and the shaded area shows the 3 standard deviation around the average yield. And compared with the previous slide, when irrigation is used, the shaded area does not expand over time. That is, the variability of corn yield does not increase as the variation of precipitation getting larger. Therefore, the irrigation do reduce the variability of corn yield. And similarly, for soybeans, this slide shows the variability of soybean yield without irrigation. And we can see that the variability of soybean yield increases as the variation of precipitation getting larger. But when irrigation is used, the shaded area does not expand over time. It means that the variability of soybean yield does not increase as the variation of precipitation getting larger. So irrigation reduces the variability of soybean yield as well. Since standard deviation is a measure of absolute variability, so we also calculate the coefficient of variation, which is a measure of a relative variability. And this table shows the coefficient of variation for crop yields with and without irrigation under 4 climate scenarios in 2017. The second column and the third column are for the corn yields. The second column shows coefficient of variation without irrigation, and the third column shows the coefficient of variation with irrigation. And we can see that the coefficient of variation with irrigation are always lower than those without irrigation. And similar results for the soybean yields. The coefficient of variation for soybean yield with irrigation are always lower than those without irrigation. So again, we find that the irrigation reduce the variability of crop yields for both corn and soybeans. So based on the above results, we can summarize the 3 key findings in the second sub-questions. So first, we find out the irrigation increases the average crop yield and reduces the yield variability. And second, the crop yields gain more from irrigation in the 3 RCP 8.5 climate change scenarios when the variation of precipitation becomes larger. And irrigation seems to have larger effect on corn yields than soybean yields. Now let's look at our third sub-questions. How often might farmers use irrigation for corn and soybeans? And for this question, we also only consider the variable cost of irrigation. First, let's look at the frequency of irrigation for corn in each county. And this figure shows the number of county years of irrigation over 51 years for corn across the 29 started counties. And this figure has 4 panels, which shows the results in different climate scenarios, base, C1, C2, and C3. And in each panel, the x-axis shows the 29 counties, and the red color represents the county located in Southern Ontario, and the blue color represents the counties located in Western Ontario, and the yellow is for Central Ontario, and the green is for Eastern Ontario. And the y-axis shows the number of years using irrigation over the studied 51 years. And in the figure, we can see that counties with red color has more irrigation years than other regions. It means that Southern Ontario has more irrigation years per county. Furthermore, we can see that counties with blue color has larger range of irrigation years. That means the irrigation years per county is more variable in the Western Ontario. And this slide shows the frequency of irrigation for soybeans. And we can see that for soybeans, the irrigation years per county are relatively less variable compared to corn that we have seen in the previous slide. The previous 2 slides show the results across 29 counties, but those 2 figures are hard for us to find the difference in results under 4 climate scenarios. So we sum up the irrigation years for 29 counties over the 51 years. We would like to know what the total county years of irrigation are for the 29 counties over 51 years for the 4 climate scenarios. And in the figure, there are 2 panels. The upper one is for corn and the bottom one is for soybeans. The x-axis lists the 4 climate scenarios and the y-axis shows the total county years of irrigation. So for corn, the total county years of irrigation ranges from 1,000 to 1,200. And for soybeans, the total county years of irrigation ranges from 1,200 to 1,300. So irrigation county years are higher for soybeans than for corn. And for both corn and soybeans, irrigation county years are higher in the climate change scenarios than in the base. In addition, the irrigation county years reduces when the variation of precipitation becoming larger. So at the first glance, this result may surprise us because people might expect to see the irrigation county years increase as the variation of precipitation becoming larger. But recall the comparison of precipitation distribution among the climate change scenarios. We found that the probability of dry events increases as the precipitation variation becomes larger, but the probability of wet event increase as well. So this result might be because the offset between the increases in probability of wet event and the increase in probability of dry event. So as a result, the frequency of irrigation decreases with the variation of precipitation becoming larger. As I mentioned earlier, to answer this question, we consider the variable cost of irrigation only. In addition, the variable cost of irrigation might vary in future. So we conducted sensitivity analysis on variable costs and only focus on the frequency of irrigation results in C1 scenario, since the frequency of irrigation in this scenario is the highest. This figure shows the irrigation county years for 29 counties over 51 years with alternative values of variable cost. And the upper panel is for corn and bottom one is for soybeans. The x-axis lists the three different values of variable cost. The y-axis lists the total county years of irrigation. And in the figure, we can see that as the variable cost increases, the irrigation county years decreases. For example, when variable cost increases from 1 cent to 3 cents per cubic meter, the average number of county years of irrigation falls by about 5 years for corn and 8 years for soybeans. So we can also tell that irrigation county years for soybeans is more sensitive to changes in variable cost than corn. So based on the above results, we can summarize these several key findings. So first, in terms of the total irrigation county years, the frequency of using irrigation for soybeans are higher than the frequency for corn. And in terms of the irrigation years per county, the frequency of using irrigation for corn vary widely across counties, but for soybeans, that frequency are less variable across counties. And when we change the variable cost, if the variable cost increases, the irrigation county years decreases. And for soybean, the irrigation county years are more sensitive to changes in variable cost than corn. So our fourth sub-question is it economically feasible for crop farmers to use irrigation as a climate change adaptation strategy in Ontario? And for this question, we consider both the variable cost and fixed cost of irrigation. Before I show you the results, first I would like to talk about the fixed cost of irrigation equipment and replacement that we use. As I mentioned earlier, irrigation equipment is not widely used for corn and soybean production in Ontario, so we do not have the actual fixed cost of irrigation equipment and replacement. So based on these assumptions, we initially assume that the fixed cost of a field crop irrigation system is $2,941 per hectare. But many factors could affect the fixed cost of irrigation in the future. For example, the costs of equipment might fall with higher levels of irrigation adoption. And also the competition among suppliers might reduce the equipment costs. And the irrigation equipment might become more efficient, and the better irrigation practice management could also reduce the fixed cost. For example, the irrigation equipment might be used for multiple crops in a given year. So in our simulation, we consider reductions in fixed costs of 50% and 25% of the initial assumed values. So we have seen this cost parameter table before, and here I show it again just to explain that for the fixed cost of equipment and replacement, we use the 50% of the initial assumed value as a default value, but in the meantime we use other two alternative values of the cost of equipment and replacement to do the sensitivity analysis. Now let's look at the results for the sub-question. First, let's look at the effect of fixed cost on the economic feasibility of irrigation under the 4 climate scenarios for 2020 to 2070. In this figure, we have 3 panels, and each panel shows the results with different equipment and replacement cost values. And the x-axis shows the climate scenarios, and the y-axis shows the number of counties where irrigation would be profitable. So in this figure, we can see that when the equipment and cost falls, the irrigation would be profitable for more counties. So for example, at the cost with the initial assumed value, the irrigation would be profitable for only few counties in C2 and C3 scenarios. And at the cost of the 50% of the initial assumed value, the irrigation would be profitable for only some counties in the RCP 8.5 climate change scenarios. However, at the cost of the 20% of change scenarios, the effect of fixed cost, we can tell irrigation would be profitable for more change scenarios, and also it will be profitable for more counties as the variation of precipitation increases. This slide shows the effect of on-farm infrastructure cost on the economic feasibility of irrigation. And the on-farm infrastructure cost refers to the cost of drilling a well or building a pond. And in this figure, we have 3 panels with different values of the on-farm infrastructure cost. And the x-axis shows the climate scenario, and y-axis shows the number of counties where irrigation would be profitable. And in this figure, we can see that higher on-farm infrastructure costs would reduce the number of counties where irrigation would be profitable. Except for the fixed cost, the variable costs also have an effect on the economic feasibility of irrigation. So in this figure, we have 3 panels with different values of variable cost. And from this figure, we can see when the variable cost of irrigation increase, the irrigation will be profitable for fewer counties. And when the variable cost is 1 cent per cubic meter or 3 cents per cubic meter, the irrigation will be profitable for some counties. However, not for the variable cost of 5 cents per cubic meter. The economic feasibility of irrigation also changes across time. So this slide shows the economic feasibility of irrigation across 3 sub-periods of the time period from 2020 to 2070. So this figure shows 3 panels with 3 sub-periods. The first sub-period, the second one, and third one. So from this figure, we can see the irrigation becomes more attractive to farmers in this third sub-period. Based on the above results, we can summarize that at current costs and with current climate conditions, it's attractive to feed producers across Ontario. However, if the costs are becoming lower and the climate becoming more variable and more extreme, then the irrigation would be more economically attractive as a climate adaptation strategy for Ontario field crop producers in the future. And also, the irrigation might be more attractive near the end of the time period considered in this study. Our last question is, how much water might be used for irrigation when irrigation is economically feasible? So we will consider both the variable irrigation for this question. This slide shows the annual irrigation volume for corn under the 4 climate scenarios for 2020-2070. And in this figure, we have 4 panels shows the results with different climate scenario. And for the x-axis of each panel, it shows the studied 29 counties, and the y-axis shows the average annual irrigation volumes. And the red color represents those counties located in southern Ontario, and the blue one is for Western Ontario, yellow for Central Ontario, and green for Eastern Ontario. So in this figure, we can see that for corn, the counties in Southern Ontario would generally use more irrigation waters. And also the average annual irrigation volume would increase in more extreme climate change scenarios. And this slide shows the irrigation volumes for soybeans, and the results are quite similar with corn. So we can see that for soybeans, counties in southern to the irrigation area times the irrigation volume per area. And this figure shows the soybeans. So from this figure, we can, and this results in the wide variation in the irrigation volumes across counties. So instead of looking at the total irrigation volume, this slide shows the irrigation rates for corn, excluding the effect of the cropland area. And in this figure, again, we have 4 panels represent the climate scenarios, and the x-axis for 29 counties, and y-axis shows the irrigation rate for corn. And in this figure, we can see for corn, the counties in southern Ontario generally would have higher irrigation rates than other regions. But for soybeans, the irrigation rates are relatively less variable across counties compared to corn. The previous several slides present the volume of irrigation water when only the variable costs are considered. So that means the economic feasibility of irrigation haven't been taken into account. So now, when the fixed cost is considered, that means when the economic feasibility of irrigation is considered, how much water might be needed. Based on our simulation results in the CFI scenario, the most extreme climate scenario, an average of 5 counties out of 29 in Ontario will find irrigation economically attractive. So if these 5 counties with the largest irrigation volumes find irrigation economically attractive, then their irrigation volume would constitute approximately 1% to 14% of annual precipitation in each county, respectively. So we can look at the figure on the right. For the county 2, the irrigation water volume accounts for 14% of annual precipitation. And for the county 4, it constitutes 12% of the annual precipitation. And for the county 20, it has quite low percentage, which only accounts 1% of annual precipitation. So generally, they are a small percentage. Low irrigation shares of annual precipitation amount. The concerns in terms of whether irrigation conflict with other water usage in dry years depends on some other factors. For example, the low water response regulation in Ontario restricts the total amount of water available for human use in dry years. And also, we don't know how much water would be required in other sectors in the dry year. In addition, the distance between urban and rural areas affects the degree of water use competition. The closer the distance, the more tense the competition. And the last point could be the comparison of green water and blue water. Irrigation mainly use green water, while the urban water mainly use blue water. So can we better manage the green water to reduce the competition of water use? So these are the questions that we still need to investigate. So in conclusion, these are the main findings in our project. So first, the projection of changes in temperature and precipitation with high greenhouse gas emission would not result in appreciable threats to corn and soybean yields in Ontario for 2020 to 2070. And the irrigation would increase crop yields and reduce the crop vulnerability to climate change. The economic feasibility of irrigation as a climate change adaptation strategy would be greater under more extreme climate scenarios. And when the fixed and variable costs are taken into account, the potential irrigation volumes are small at provincial level. And the irrigation seems to become more attractive for the later years in our simulation period. And the economic feasibility of irrigation for field crop production is sensitive to fixed costs. So at the end, I would like to appreciate the OMEFRA for funding our project. And here are the references that you may feel helpful.
So thanks for your listening. If you have any questions, I will be happy to take.
Thanks so much, Chin, for that presentation. I really appreciated it. We had a few minor sound issues. Folks, if you want to write in any questions that you have for Chin in the question area, you can see that on your control panel. There should be an area to ask questions. While we're waiting for people to write a question in, I have a question for you, Chin. So in the end, you're showing that there's just a few counties that, when we consider both the fixed costs and the variable costs, that we really see the benefits of those investments. And what conditions might make irrigation more favorable? Like when I'm talking to specific growers, what conditions on their in their situation might make it more favorable?
So first, in terms of the climate factors, if the climate change becomes more extreme, and especially the variability of growing season precipitation getting larger, then it will make the irrigation being more profitable or more favorable, more attractive to the crop producers in Ontario. And also, if the costs of irrigation could be lower, then it would be more profitable for farmers to use the irrigation. For example, if the technology development in the future could lower the price of the equipment, or the competition between suppliers could result in the fall in the price, or maybe more farmers adopt the irrigation equipment, so the price could fall down. And also the better irrigation management could reduce the fixed cost per hectare. Maybe it will make the irrigation more favorable.
Great, thanks. Another question for you. So your research looked at sort of the average on a county basis. Do you have any sense about the level of variability within a county?
The variability of
the yields and the impacts.
Yeah, unfortunately, we only have the county level data. So in terms of the more disaggregate level, it's really hard to tell. But generally in the Southern Ontario, the counties in the Southern Ontario, it seems that the irrigation will be more favorable to them, more attractive to them if the climate scenarios become more extreme and the precipitation variability getting larger.
I see we have a number of colleagues on the line from Quebec. They also have a humid climate like Ontario. how applicable do you think your results are to our sister province?
So I'm not very familiar with the climate in Quebec, but as you said, they have the similar climate to Ontario. So based on that information, we also need to see what's the crop yield in that province. And based on that information, we need to do more analysis to answer these questions. Because I cannot simply say yes or no, because it depends on how profitable the irrigation would be used on the corn and soybeans, and what main grain crops are planted in Quebec. Yeah.
And in order to do the analysis, we would need to have sort of county level or regional level corn and soybean yield data, historical, in order to, but then it could be applied using your model.
Yes, I believe so. So first, as you said, we need the historical data based on the corn yield, of the soybean yield, and maybe other crops. And also we need to have the historical climate data as well to help us estimate the crop response to the climate, to the crop price, and other factors such as the land quality, and also the carbon dioxide concentration as well, because we upgraded our model and we include these factors, which not many crop yield models included this factor. So
Okay.
we need all of these factors to help us estimate the crop response to the climate, to better estimate the crop response to the climate. And then we are able to forecast the crop yields in the future, and by how much the irrigation could increase the corn and soybean yield. Then we could understand the benefits from the irrigation and compare it to a cost to see if the benefit of irrigation could outweigh the cost.
So I have one more question. The climate data that you used, the historic data, it was from NRCan?
It's from Natural Resource Canada. Yeah.
And the climate change projections were also done by Natural Resource Canada?
Yes. Yes, they have a database that each like they interpret the historical weather station data, and their database are based on those I think more than 3,000 weather station data, and they have a model to better estimate the weather data. Depends on what regions we started. So because the weather station data, they only measure the weather data in a location, but we are able to get the weather data depends on what regions we would like to study for a larger region. For example, I can get the weather data for Wellington County. I can get the weather data for Breton County. So it covers a wider range, and we don't need to do the average to calculate the mean of the weather data for across each weather station data.
Are there any other questions from the audience? Okay, well, we're just past 3 o'clock. Chin, I want to really thank you for this work, and I encourage folks to be in touch with Chin if you have further questions. I think this is really exciting research and is going to provide some real insight for our growers in Ontario. And you know, making decisions about these types of major investments is really a challenge, and particularly given the uncertainty with climate change. So this is great. Folks, I just want to invite you to join us again looking at the precision irrigation work in field crops in southern Alberta that will be brought to us by Dr. Willemijn Appels on January 21st. So I hope to see many of you again on the line at that time. Thanks everyone for joining. Thanks Chin, and thanks to CANCID CWA for this webinar series. Have a great afternoon, everybody.
Bye, everyone.